This is the analysis catchments mini workflow. One of the key analyses that we try to produce on a piece of topography is not just where water is moving and flowing to and from, but also the different watersheds or catchments on our site and in our topography. LandKit has a great tool that allows us to produce this analysis on our site quickly and efficiently in a way that responds directly to any changes that we're making to our site. So if we were to modify this topography to produce a different type of landform, we will get results that respond and update live according to these changes that we're making. In this case, I'm changing around the form of the topography and creating different types of catchments on the site. Each color that you're seeing represents a different catchment area on the site itself. The way it does this is by producing an environmental analysis inside of a boundary that we create, and then it produces grid flow lines that might be familiar to those who have used GIS-like software to produce flow lines. And that will help the software delineate the different ridges that divide where water is flowing from and to ultimately produce the catchment boundaries that we see here. We also have the ability to take those catchment boundaries and produce actual shapes out of them, which you're seeing a representation of down here. These catchment zones can then be utilized in other areas or software or certain types of analyses with other tools in LandKit as actual boundaries that represent those catchments. So what are some of the ways that we can manipulate this analysis? In the RCP panel, you'll see that we have the ability to affect the level of detail of analysis that's taking place using the cell size. A smaller cell size is going to produce more analysis points across our site, or in this case, our environment boundary. And then those analysis points will produce a higher resolution image of analysis. The larger the value is, the blurrier that analysis image becomes. And you can see the number of flow lines here have reduced because we've increased the cell size spacing. That will produce a lower level of analysis, but it will also produce a faster process for the analysis. So on a much larger site, you might need a larger cell size. But if you have a powerful enough computer, you can utilize different cell size strengths at any point. We also have the ability to elevate this to our topography and even affect the smoothing strength of the boundaries of our catchments from the shapes that we're creating down here, where a lower smoothing strength or higher smoothing strength will affect the edge between the catchments as actual shapes. So if we want a more rigid curve, we can decrease the smoothing strength and steps. Or if we want a much more organic curve between these different catchment zones, we can increase the smoothing steps or smoothing strength. Now, in our layers in our Rhino file, you'll notice that we have, in addition to our topography and our environment boundary, we also have basins and pipes. The pipes allow us to connect different catchment areas together. So if we're trying to understand different types of catchments and their relationship to each other, for instance, I decrease the cell size to increase the quality of analysis, and I'm starting to get a slightly different picture of the catchments on our site with this higher resolution. Perhaps I know that these dark blue and black catchments are actually connected by a pipe that leads to the same outflow. So in that case, I want that to be represented in my image of my catchments. So on the pipes layer, I'll draw a curve that begins in one catchment and ends in the other. And then it will connect those two catchments together as a single catchment based on the underlying pipes that connect them together. Additionally, basins allow us to do something a little bit more similar, but in a more generalized way. In this case, if we look at our topography here, we can see that both of these two light and medium blue catchments are coming and meeting in a similar basin location, but a slight change in the topography between these two catchments is what's causing them to create two different catchments. But perhaps we know that this is supposed to be a single basin. So if we draw a curve that represents that basin by creating a closed curve that represents where we know we are implementing a basin, we can connect any catchments that flow within that basin boundary together. So however we form this landscape and adjust the topography, the boundary of this basin will stay the same, and any water flow that passes from one catchment into this basin will connect to the other catchments that are also flowing into this basin. So let's take a look at what this appears like in the Grasshopper script. In here, you'll notice that we have a very basic setup for creating our environmental analysis. We have an environment boundary, a cell size for the quality of analysis that we're producing, and our topography being fed into a create environment component, which creates the underlying analysis points that will be producing the image and analysis that we're creating. Then we're feeding that into an add catchments layer, which takes in basins as a single curve that is closed and pipes that connect multiple basins together or catchments together by using the endpoints of the curve. Our outputs produce a variety of different geometries and values. We have the environment output with that catchment embedded that we can then preview using a draw layer as mesh. But we also have the grid flow curves that are based on the cells of our environmental analysis and the colors of those curves. We also have indices indicating the number of different catchments with specific indices to label them, as well as the area of each catchment and the high and low points within each catchment as well. And then we are simply using the draw layer as shapes component in order to produce the shapes here that we can bake out and produce surfaces from for other types of analysis.